Of all the forces of nature, gravity seems to be by far the weakest. It is also the one that has been cogitated by philosophers and scientists for the longest amount of time, yet is still regarded as the least understood. The strength of gravity is dependent on the fractal depth, and so too are the other forces. When a fractal depth becomes deeper, all the forces of nature increase, but the differences in their strength become less, until at the fractal prime of the singularity they become as one. I believe gravity is the most important force to understand, and I hope this video will help in that regard. In this video I want to demonstrate how I came to believe that gravity is an emergent property of transfinite spacetime. It is said that Sir Isaac Newton was avoiding the city at the family farm to lessen the chances of getting the plague when he was struck by the idea of gravity as he witnessed an apple fall to earth. Pondering what it would take to defy the force of gravity without the aid of wings, the way that the moon does, he realized that a cannonball will fly long enough to give someone at a distance a bit of a headache. In this thought experiment, it is easy to see that if you get your cannon high enough and fire it with enough force, the cannonball will travel far enough to take advantage of the curvature of the earth. Fire it fast enough and it'll keep on falling without getting any closer to the ground. It is easy to see that what makes apples fall is also responsible for keeping the moon in the sky. Galileo, in a thought experiment, concluded that two objects of different weight will fall at the same rate. On the moon, where there is no air, even a hammer and a feather will fall together. And this was actually demonstrated on the moon during an Apollo mission in 1971, and recreated here by our intrepid Bob. The strange thing about gravity is it increases the velocity of a falling object without it feeling an opposite and equal force associated with acceleration. Recently, Felix Baumgartner, following in the footsteps of Joe Kittinger, leapt back to Earth from high up in the atmosphere, with the black sky above, wearing a pressurized spacesuit to stop blood boiling in the near vacuum and a parachute for the final leg of the intended descent. They have jumped from the highest step then known to mankind. In the upper stratosphere, the air is so thin that Joe's initial descent did not even rustle the fabric of his spacesuit. With 99% of the atmosphere far below, he had no sense of falling at all, until he looked up at the balloon as it appeared to shoot up into space. He felt no acceleration, yet the speed of his descent climbed to 990 kilometers per hour, and Felix, on his jump, was the first person to exceed the speed of sound without an aircraft. Had they been dropped in a similar way onto a planet with no atmosphere, they would feel no effects, except possible apprehension of the all too brief terminal planetary resistance. Forgetting time and my fractal depth for the moment, what does it mean when we say that the universe is infinite in size? An infinite universe is one that has no boundary. Infinity is not a number or size, it is a state of being that cannot be quantified, an abstract notion. I think most will understand that the term half infinite makes no sense. You cannot divide infinity. In the same way, you cannot multiply infinity. You may argue that some things are countably larger than others that are infinite. For instance, you could argue that the decimals are countably larger than the integers. Infinity, though, is not countable, and in that scenario the decimals are just a fractionalized part of the infinite integers. It is also argued that a finite universe can be unbound, like the surface of a sphere. If we, for instance, take the x-axis and travel in the x plus direction, we will come back to where we started from the x minus direction, and the same goes with the y dimension. But on a two-dimensional sphere, the two dimensions have a curvature in the z dimension, that is either the z plus or the z minus. For an unbound finite universe with three spatial dimensions, each dimension would have to circumnavigate the other two dimensions in both the plus and the minus simultaneously. For instance, the x and y would have to have a curvature in the z. In this case, the z plus. And how does the z curve? You cannot simultaneously curve all three dimensions spatially. The ball analogy supposes that you could if you use the fourth dimension, but the fourth dimension is temporal and not spatial. For instance, would you curve the x dimension in the z plus, like before, or the z minus? Actually, the x dimension would have to curve in both the z plus and the z minus, and both the y plus and the y minus, or the x dimension would have to have an edge, and this is a problem with all three dimensions. It may work for a computer game, but not in a finite universe. The way infinity was explained to me was in a thought experiment where we imagined two infinite parallel lines, and then imagine that the place they would eventually meet would be at infinity. The point was, they never do actually meet. But if the dimensions of the universe are shrinking in a scalar way along with time, then perhaps they do, at the end of time. If in an infinite universe we take the x-axis and extend it to infinity in the x plus, then just like the analogy that two parallel lines meet at infinity, then either end of this single dimensional line could also be analysed as to meet at infinity. But the x plus and the x minus of this line, unlike the finite example, do not need to transcend the other real dimensions z or y. Their meeting is abstract or imaginary. The circle they draw has no curvature left or right, for this is an abstract imaginary circle, as it is imaginary in the z dimension. In fact, it is imaginary dimensionally in all three dimensions, making the single x dimension multidimensional, only in a complex and abstract way. Each real dimension has an imaginary multidimensionality. X, Y, and Z. When a star of about 8 solar masses or less, like our Sun, runs out of hydrogen to fuse, it will expand into a red giant. These fuse helium into carbon until it eventually loses its battle with gravity, sheds the outer layer in a massive explosion, and the core collapses into a white dwarf star. a compact star that appears to be about the size of planet Earth. It seems to me that this star has been forced by the blast down the fractal depth, as if it has obtained a relativistic velocity in all three dimensions at once. It has a velocity, if you like, in the imaginary dimensions. Anything falling towards such an object would acquire a deeper fractal depth as well. For instance, imagine hovering high above the Earth, where the influence of the Earth's gravity is less. Time would be running faster. If you then gradually reduce your distance until you land on the Earth, then you will experience, unnoticeable to you, time slowing down to be the same as Earth time when you land. Would the same happen to planet Earth? If she were to fall towards a white dwarf star, would she shrink to a Sun-Earth ratio before burning up? Imagine this to be the case, and then imagine Earth falling directly towards a black hole. As the Earth falls, then just like Felix and Joe, we would not feel any increase in velocity. We would not be weightless either, as we would still be under the gravitation of the Earth. But as Earth acquires the fractal depth of the black hole, it would be shrinking dimensionally. Gravity would be getting stronger. The planet would heat up, as the same original heat of the planet would be concentrated into an ever smaller dimensional area. The stars in the sky would become further and further away, as the universe in our ever deepening fractal depth expands exponentially. Eventually, all but the black hole is beyond our Hubble sphere. As outside observers go beyond our Hubble sphere, they see us go beyond the event horizon. Things would become literally critical, as our mass would go beyond our Chandrasekhar limit and we would explode. Because distances are the property of a body of mass, distances in the direction of a massive body will always be less on a moment-by-moment basis. The curvature of space-time at any one moment is linear, a consequence of an infinite universe. An object falls because the distance between the object and the centre of the Earth is always less in the future on a moment-by-moment basis. The change in distance creates a velocity that is increased in the next moment. The object falls without experiencing acceleration. When an object is stationary on the surface of the Earth, the distance between the object and the centre of the Earth's core is still getting less and less, but is resisted by the ground. I think of this as constantly being decelerated. The fractal depth of the Earth is giving us a movement that is being continuously stopped by the surface of the Earth. The rubber mat analogy used to describe warps and curves in four-dimensional spacetime can also be used to describe three-dimensional spacetime with a fractal topological depth. We could use contour lines to indicate the depression of the mat in the same way as topographical maps indicate hills and valleys. We could use contour lines to indicate the fractal depth. Time and distance are constantly shorter towards a body of mass like our planet. It is almost like space and time are being devoured by the planet. It is not like water, though, going over a waterfall. Things are not carried along by this movement like leaves on a river, or space-time does not exist in the same way as water or air or any other pondable media. The distance to the centre of the planet is continuously getting shorter, giving an object a velocity. We now have a velocity plus distances getting shorter, compounding the velocity of a falling object. Resisting gravity, Bob, in his hovering rocket, approaches Earth and then lands. From high above the Earth, Bob will be in a higher fractal depth where Bob's time runs faster and his ruler is relatively longer than a ruler on Earth. As he approaches the Earth and lands, his ruler dimensionally shrinks to be the same as Earth size. If we look at the contour lines of the fractal depth of planet Earth relative to Bob as he descends to Earth, the contour lines get closer together but remain at equal distances apart. Counterintuitively, as the universe shrinks relative to Bob as he descends, objects like distant galaxies will become relatively further away. You may wonder why then the universe appears to expand whilst galaxies do not. Take these two neighbouring stars in a galaxy. Let's say they are the same size and at the same fractal depth. The future distance between them will be getting shorter on a moment-by-moment basis. But, being several light years apart, their past time distance increases by about the same amount. Because they are both slowly descending down the fractal depth at the same rate, the contour lines are remaining the same number between them as they dimensionally shrink relative to the past in a kind of past and future distance Lagrange point. Notice that the very distant galaxy will shrink the same, and so it will appear to the two stars as remaining the same size, but due to the comparatively vast distance to that galaxy, it becomes comparatively even more distance to both stars. In a thought experiment where I imagined myself travelling towards a black hole, wondering what my radio signals would sound like back on Earth, I imagined that as time for me slowed down as I approached the black hole, my radio message would sound like Dory doing her whale speak. But one thing that gave me doubts about this at first was the way pulsars appear to be spinning very fast, and that seemed to be the exact opposite effect. These were objects that were deeper down the fractal depth, deeper even than white dwarf stars, and so time dilation would be very noticeable. So why are they spinning so fast? Then I remembered how recessional velocities would have the effect of slowing down events. Increasing distance gave ever greater time delays due to the finite velocity of light. Even though time would be running faster, when the light was emitted, the recessional velocity would slow the events down more. A good analogy to this effect is recording a sound on a tape recorder 20 feet per minute and then playing it back at a slower speed, for instance 10 feet per minute. The faster speed recording would then sound like Dory and her whale speak. My transmission to Earth as I approached a black hole would be sent from where time was running slower, and then back on Earth where the signal is sped up to the faster rate of time analogous to a tape recording made at a slow 5 feet per minute and then playing it back at a faster 10 feet per minute, or like playing an LP record that was recorded at 33 1/3 RPM being played back at 45 RPM, the speed of a single record. So not sounding like Dory doing her whale speak at all, more like Mickey Mouse or the Chipmunks, or like something getting closer. If we were to imagine that the movement of the stars in this galaxy, represented by these yellow disks, was similar to that of the planets in our solar system, with a rotation curve getting progressively steep towards the centre, then we would expect to see something similar to this. But what we find is a much flatter rotation curve, with stars rotating almost as if fixed to a giant wheel, like this. But if we were to consider the rate of time getting progressively slower towards a supermassive black hole in the centre of our galaxy, then they do travel progressively faster towards the centre relative to their individual rates of time and peculiar distance. With transfinite time, there is no need to move the cosmological constant from the space-time curvature side of the equation to the stressed energy side, because transfinite time can make gravity both positive locally and negative holistically relative to the very distant past, and can provide the mechanism for the inflation effect. In my final video, I will link these ideas to my subatomic world and the basic building blocks of, well, my reality, and where photons exist in 3 separate monodimensional flavors